Okay, let's go ahead and get started. How many brought in questions today? Anybody?
I'm sorry.
So everybody okay then on logic and sets?
Yep.
Ready for the final on that? At least before your final review, right? The video of that is now up. Everybody see that? It's in the, if you go into content and go down to logic, which is where the final exam is also going to come up when you want it, you'll see the review of logic and sets. Okay? Now, in this class, I didn't get all of that taped because I was able to record the first Monday and then I didn't get Wednesday. So what you're going to see is actually the other class where I did it all in one period. But it's the same thing we did. In fact, I think I've got our video in there too, but it just says review of logic. So the second one says review of logic and sets. And I probably said some things differently, so if you want to look at both of them, that's fine. But the second one is more inclusive. Okay, so today we want to get started on relations and functions and possibly get into graphs by Wednesday, okay? So let's start with relations. So this is a relations quiz. We'll use it for our review. Okay, so first of all, in relations we talk about the properties of a relation. And the properties we've talked about are reflexive, transitive, symmetric, and antisymmetric. Now what are they? Well, let's review what they mean. Reflexive means that an element is related to itself. So in a relation, the way you're going to see that is a pair of A's or a pair of B's, pair of C's. But remember also that these properties are properties of the whole relation, not just of a few things in it. So if you see A's and B's and C's in the relation somewhere, for it to be reflexive, you have to see A, B, B, C, C, right? All of them have to be reflexive for the relation to be reflexive, okay? Transitive takes three different elements, and it's like a chain that's linked in the middle by the middle element. So if you had A, B, and C, you could see an A to B, and then B follows on to C, and then following, you're going to need A to C, okay? And if you see all those, every time it's possible. So make sure you're looking at how this is possible. If there's a possibility for transitivity and one of the things is missing, then it's not, then the relation's not transitive, is it? Okay? All right. Symmetric is kind of like looking in the mirror. If A is related to B, then B's got to be related to A. It takes two elements, can't be the same one, has to be two different ones. But if one is related to the second, then you've got to see the reverse of it also. Okay? Does that make sense? Yes?
So this is one of the ones that kind of got me for this exact same question. Mm-hmm. For the quiz, I thought it was transitive, symmetric, and antisymmetric. One second, let me pull out my notebook. But what made it not transitive?
Well, let's take a look at it in a minute. Okay? I'm going to do this one after we get through all of the properties. Okay? But you're right. Take a look at it. Antisymmetric. What does that mean? That means that in no case ever do you see two different elements repeated or reversed. Okay? So if there is an A to B, it cannot be a B to A. Right? So those are the properties that we have there. Now sibling. Well, let's go through sibling and take a look at it. Is sibling reflexive?
No.
No, because if you are an only child and somebody says, do you have any siblings, your answer will be no, right? Mm-hmm. Okay, so you're not a sibling to yourself. Now transitive, let's take a look at that. If you have a sibling and your sibling has a sibling, what's your relationship to their sibling? Is that your sibling too? Mm-hmm. Yeah, it is transitive. How about symmetric? If you have a sibling, are you their sibling?
Yes.
Yeah, so it's symmetric, isn't it? Is it antisymmetric? No. So it is reflexive, transitive, and symmetric. Now, were you saying that this one may not have been answered then?
No, I was foolish. I put symmetric.
One of the others, weren't you?
I put symmetric and anti-symmetric, but that's impossible.
Yes.
It was a slight mistake.
Okay. I just want to make sure the answer is right here. It's not reflexive, it is transitive and symmetric, it's not antisymmetric. Right? Okay. But let's look at some other cases here. What about parent? Can you be your own parent?
No, I don't think so.
Not likely, right?
Not yet.
Yeah. There's one case in Greek mythology, but we don't want to talk about that one. Okay, so, but overall, you're not your own parent. You cannot be. So it's not reflexive. Is it transitive? Well, here you have to define carefully what you mean by parent. If you are a parent, you have a child, and your child has a child, are you the parent of the child's child? No, you're the grandparent. Okay? So in that case, you're not the parent. We're defining parent as only one generation apart. Okay? So, it's not transitive. Is it symmetric?
Yes.
If you have a child, can that child be your parent?
No.
No. Can't reverse them, can you? Can you ever reverse them?
For a parent.
Not in the general sense, can you? So therefore, it is antisymmetric. It means it's never symmetric. There are no symmetric issues anywhere in there. So in this case, the only thing we got was antisymmetric, wasn't it?
Professor Rutherford,
Yes.
would it be possible for us to get a chance to go back through these quizzes as like a practice run for the final?
Well, that's why I'm doing this. Let's just watch the video.
Okay.
They're all there. Okay. And the reason I can't do that easily is if I go back and open them, the grading
It'll
system
change.
in D2L makes it open for grading too.
Okay.
Okay, so that's been a frustration for me. One semester I printed them all out. You'd be shocked how long it takes to print out of D2L. Okay. Which of the following properties holds for sister? Well, let's see. Can a girl be her own sister? No. If you have a sister and your sister has a sister, is that sister your sister?
Yes.
It doesn't matter whether you're a guy or a girl, right? Okay? So it is transitive. Is it symmetric?
No.
No. You know, I should change this to brothers because we've got so few girls in the class. They're the only ones
You
who
did.
get confused by this one, wouldn't they? Because they know that if they had a sister, their sister has themselves as a sister. You guys all know if you had a sister, you can't be their sister, right? But I'm not into trick questions, so this should be pretty obvious. Yes, it's not symmetric, is it? But then again, is it anti-symmetric? No, because it could be two girls, couldn't it? So therefore it's neither. There is a huge area in between symmetry and anti-symmetry that exists where it's neither. Okay. Okay, is everybody okay with that one then? It's not reflexive, it is transitive, it's not symmetric, it's not anti-symmetric. So all it is transitive. How about the empty set? Well, this is where it comes up about how do we define these properties. All these properties are defined with if statements.
And they're all false.
So, there's something that we have to be aware of, and that is that when you have a set or a relation, do this different. Even like that. We call A, B, and C are elements of the poset. The poset is the set from which all of the individual elements come from. Okay? So knowing that then, when we go through the formal definition of reflexive, we would say that if the element A is an element of the poset, then AA would be an element of the relation. That makes sense? It's a way of talking about those individual elements is what that means. So, is the empty set reflexive?
Yes.
Yes, because remember the if statement. If the first part of the if statement is false, what do we know about the if statement?
Everything is true.
It's true, right? Okay. So therefore, it is reflexive because there is no element in the poset. It's empty also. So is it transitive?
Yeah.
Well, transitive says if AB and BC are elements of the relation, then AC must be a relation, or must be an element of the relation. Is there ever an AB or BC combination in the empty set?
No.
No. Therefore, the first part of the if statement is
False.
false. Therefore, it's transitive. Symmetric, same thing. If AB is an element of the relation, then BA must be an element of the relation. But there is no AB. Therefore, it's symmetric. What about antisymmetric? If AB is an element of the relation, then BA is not an element of the relation, is the definition. Oh, what about the first part? Is that true or false? It's false. There is no AB. Okay. This is one of those cases where it's reflexive, transitive, symmetric, and antisymmetric. It's all of the above, and it's because of the property of the if statement. That's why that happens. Okay. Any questions on that? Okay. Don't get caught on that one. Now that brings up this one, which is kind of interesting. I've got a relation there, AA, BB, CC, and DD. Is that reflexive? Isn't it obviously reflexive? Everything's related to itself, isn't it? So it's obviously reflexive. But let's look at transitive. Transitive says if there's an AB and a BC, then there must be an AC. Is there an AB and a BC chain in this?
No.
No. Therefore what?
It's false. I mean, it's true.
It is transitive, yeah. The first part's false.
Mm.
Yeah, it is transitive. What about symmetric? Is there an AB with two different elements?
No.
No. Therefore, it is symmetric. And antisymmetric, again, is there an AB?
No.
Therefore, it is antisymmetric. So this one's not the empty set, but it is a set or a relation that is all of the above. Okay? Does everybody see why? Again, definition of the if statement. Okay. Okay, transitive closure. What is the transitive closure of this relation here? Well, the transitive closure says if there's the first part of the if statement, in other words, the linkage from an A to a B and a B to a C, if that's there, but the conclusion is not there, then by adding the conclusion, you've got a transitive, right? And the transitive closure then is the smallest relation set that would make this transitive. So let's look at it. The only opportunity I have for transitive, isn't it 1 to 2, 2 to 4? Therefore I need what?
1 to 4.
1 to 4. So that's all I need. And we don't add anything else. So right here I have 1 to 2, 1 to 3, 2 to 4. That's the original. Plus 1 to 4. This would be the transitive closure. Now down here, notice there's 1 to 2, 1 to 3, 2 to 4. That's the original. And the 1 to 4. And we've also added 3 to 4. Did we need 3 to 4?
No.
No. Notice that 3 to 4, this is transitive, it's not, because we have 1 to 3, 3 to 4, 1 to 4. So this is transitive, but it's more than we needed for closure. So transitive closure is the minimum you need. Okay? Everybody okay on that? Okay. An equivalence relation, the best way to remember equivalence relations is to remember the equal sign. The equal sign is the most trivial version of an equivalence relation, right? So in the equal sign, is every value on an equal to itself? Is n always equal to n? Is I always equal to I?
Yeah.
Of course, right? So it is reflexive, is it not? Okay. What about transitive?
Yes.
Is if I is equal to j and j is equal to k, is I equal to k?
Yes.
Of course it is. All right. And what about symmetric? If I equals j, does j equal I?
Yes.
Yeah. What about antisymmetric?
Nope.
No, not in that case. So, we're looking for a relation here that's reflexive, transitive, and symmetric. Well, up here I have 1, 1, 2, 2, 1, 3. Let's see. Is it reflexive?
Yes.
Where's 3, 3?
Oh.
Remember, it has to have every opportunity, okay? So 3, 3 is not there, so it's not reflexive. Here we have 1, 2, 2, 2, and 3, 3. And 1, 2, and 3 are the only poset numbers, aren't they? So I do have reflexivity, 1, 1, 2, 2, 3, 3. What about transitivity? Let's see, I've got 1 to 2, 2 to 3.
Oh, yeah,
do I have 1 to 3? Yeah, I have 1 to 3. Let's see, do I have any other, yeah, I've got, no, I think that's everything. What about symmetry? I've got 1 to 2, do I have 2 to 1? I don't have 2 to 1, do I? So it's not symmetric. Is it antisymmetric? It looks like it's antisymmetric, doesn't it? But that's not an equivalence relation. All right, down here, I've got the 1, 1, 2, 2, 3, 3. I've got 1 to 3 and 3 to 1. There's your symmetry. Is this transitive? You can tell me, is that one transitive?
Yes.
And why?
If statement's false.
The first part of the if statement is false, isn't it? I don't have the beginnings of a chain here. So it is transitive. And down here, notice I have 1 to 3, but I don't have 3 to 1, so it's not symmetric. So this is the right answer. It's the right answer, but be careful. The reason it's the right answer is because the transitivity is true because the chain, the beginning of the chain is not there. But it is reflexive and it is symmetric. So that would be your answer. Does everybody see that? Everybody not? Yes, ma'am.
So for symmetry, it only has to be one pair that's symmetric, right? Not all of them?
No, all of them. All of the opportunities. In other words, this one is not two different elements, is it? And that's what we need. We need two different elements. So I look through here. Here's a different element, 1 to 3, right? So therefore I must have 3 to 1. Yeah, I do have 3 to 1. That was the only opportunity for symmetry. Now, if I'd had a 4 to 7, I'd have to have a 7 to 4 also. Does that help?
Yes.
Yeah, because that makes it look like you only needed 1. But you only needed 1 because there is only 1. Okay. Okay, total order. Now, we didn't have any questions on here on partial order, but partial order and total order are very similar. To be an order, partial order for instance, we must be transitive and anti-symmetric, right? Okay? I think we have to be reflexive. It's reflexive, transitive, and anti-symmetric. It's like standing in the line at Walmart at the cashier. Okay? The difference between a partial and a total order is, for a total order, every possible pair must be there. Everything must be related to everything else, is another way of saying it. All right? So this is a total order. So let's look at it first. Is it reflexive? 1 to 1, 2 to 2, and 3 to 3. This one's reflexive. Is it anti-symmetric? No, this one's symmetric, isn't it? So therefore, that's not it. Here, I don't have all the reflexives I needed. Here I've got 1 to 1, 2 to 2, 3 to 3. I've got 1 to 2. I do not have 2 to 1, that's good. I've got 2 to 3. Do I have 3 to 2? No. So here's 1 to 3 and I don't have 3 to 1. So this one is anti-symmetric. What else do I need to check for?
Transitive.
Transitive.
And it is.
1 to 2, 2 to 3, 1 to 3. Yeah, so it is transitive. Now, is everything related to everything else? Well, 1 is related to 2, isn't it? Is 2 related to 3? Yeah. Is 1 related to 3? Yeah. So, this is total order. Okay. Did everybody see that? Down here, we don't even have reflexivity to it. Okay. Okay, which of these is a total order? Is this one? This one's not reflexive, is it? How about this one?
It's
Got
the empty
3 to
set.
3, 2 to 2, 1 to 1. I have a symmetry going on here, don't I? That's not it. What about this one?
Yeah.
Uh-huh. Trick, isn't it? It's reflexive, it's anti-symmetric, and it's transitive. Does it matter that it's also symmetric?
No.
No, it's not part of the definition of total order. Total order is defined as reflexive, transitive, anti-symmetric, and all elements that are in there are related to every other element. But that's taken care of by the fact there are no elements, right? And then this one fails on all counts. Of course, this question could have been answered by eliminating the others, right? But yes, the empty set is a total order. Okay, which of the following is a total order? Well, let's see. How about this one? Do we have reflexivity?
Yes.
We do, don't we? We've got AA, BB, and CC, and they're the only elements mentioned. Do we have transitivity? I've got B to C, C to A. Do I have B to A? I do, don't I?
Yeah.
Be careful, they don't have to be in order.
Oh.
Okay? So I've got B to C, C to A, B to A. Now, do I have any other? No, I don't have any other opportunities to be transitive, do I? Is it anti-symmetric? It is, isn't it? And is A related to B somewhere?
No. Yes.
Yeah. Is B related to C somewhere? Yeah. Is A related to C somewhere? Yeah. So therefore, it is a total order. Okay? So that's the one. Okay. So, are we okay on relations? We got that down pretty well? And again, the final is different questions, but I've pretty well taken it from what's on the quizzes. So if you've got these quizzes down, you're probably in good shape for the final. Oops, did that. So let's look at functions. Remember, we talked about functions in the terms of what is a function. We talked about one-to-one and onto, right? And a one-to-one correspondence. So those are the types of things we're going to be looking at here. So, is this a function? Yeah, I see a lot of yeses. Yeah, it is, isn't it? Because every element over here is in the function, right? And only once. Because remember, these cannot be repeated. Okay. And that's the big definition of function. Is that a function? No. And it's not a function because 4 is related to 2 and related to itself. You cannot do that, okay? In a function, remember the vertical line test on graphs? It's really the same thing, isn't it? Vertical line test says a member on the x-axis can only have one y value, not 2. Okay? What about this one? Is that a function? No. What's wrong with it? Yeah. We have a member here, 4, in the domain that does not have a corresponding element in the codomain. Okay? Remember the terminology, by the way, is this is the domain, this is the codomain, not the range. What's the difference between a codomain and a range? Well, if this were a function, 1 and 3 would be the range. 2 and 4 would not. Because the range is similar to the definition of the domain. It must have arrows coming to them, okay? But in the range, of course, you can have 2 coming to the same one. Okay? The range is a subset of the codomain. Okay. The function f of x equals x plus 1, where the domain and codomain are the set of natural numbers, is onto. Is that true? Well, what does onto mean? In the case of onto, every member of the codomain has something coming to it. Okay, that's the definition of codomain, or of onto. The codomain is covered, completely covered. There are no elements without an arrow coming to it, for instance. So the codomain must be completely included in the function for it to be onto. Well, let's see. And what are the natural numbers? Anybody remember what the natural numbers are? They're the counting numbers. 1, 2, 3, 4, 5, 6. Okay. So, is this going to be onto? Well, let's start with the x's. What's the first value in the natural numbers?
0.
It's argued whether it's 0 or 1. But let's say it's 0, okay? So what's the first value of the function then?
1.
1. Uh-oh. If the domain and the codomain are the same, we've got an element in the domain 0 that does not map to 0 in the codomain. What maps to 0 in the codomain? Nothing. It never gets covered, does it? So we have a member in the codomain that's not covered. All right? So therefore, it is not onto. False. Does everybody see that? Now, is the range onto?
No.
Always.
Yeah.
Because the range is defined as all of the results of a function. Okay? So the range is always onto. Okay? So another way of defining range is you could say the range is the set of elements of the codomain that has a result from the function. Okay? Or if the function was written as ordered pairs, then the range are all of the elements that are in the second position anywhere in the function. Okay? Gee, I've already answered this one. The range of a function is identical to the codomain of the function. Oh, if the range of the function is identical to the codomain of the function, then the function is onto. It is, isn't it? Because we just defined the range as that element, that subset of the codomain which is onto. Well, now it's the same thing. So that means that the whole codomain is covered. How about this one? The cardinality of the domain of a function is equal to that of its range. What is cardinality? Cardinality is the number of elements in the set. Okay? It's the size of the set by counting the elements. So is the cardinality of the domain of a function equal to that of its range?
Not necessarily,
Not necessarily. And why would it not be?
because two elements in the domain could use the same element in the range.
Exactly. Okay. You could have, here's the domain, here's the codomain. You could have 1, 3, 7, 2, 4, and you could have this, couldn't you? Or let's make it even onto. Did we say it was onto? Okay. So now, here is the range of the function, isn't it? Because that's where all the arrows are going. But this is not the same size as this. It's smaller. Okay? The cardinality of the domain of a one-to-one correspondence is equal to that of its range. What about that? Is that true?
True.
The answer is yes. Because a one-to-one correspondence is not only one over here to one over here. In other words, the arrow can only go to one. It's also onto, so it's completely covered. This could even be more powerful if we said the cardinality of the domain of a one-to-one correspondence is equal to that of its codomain, right? Because the codomain is fully covered because it's one-to-one and onto. So, which of the following is an onto function? Is the first one an onto function?
Yes.
It is, isn't it? Is it a function, first of all? You always want to look over here first, okay? It is a function because each one of these only has one arrow coming out of it, and this is completely used. Okay? Let's look at the others because of their value in studying. What about the second one there? Is that, I put it up to them. Do y'all see this all well now? Is this one an onto function? It isn't because the 4 is not used. Okay? What about this one here? Is that an onto function?
It's not a function at all.
It's not a function at all because the 4 here has 2 arrows coming out of it. It's related to 2 different values in the codomain. And lastly, this one. Well, this one isn't even a candidate. It's not a function because 4 is not in the function. And of course, the 2 and the 4 aren't covered over there. Okay. Which of the following is a one-to-one correspondence? Is this first one a one-to-one correspondence? First of all, is it a function?
Yes.
It is a function, right? But it's not a one-to-one correspondence. Let's look at that second. Is the second one a one-to-one correspondence?
Yes.
This one is, isn't it? Because, first of all, it is a function. All of them have arrows coming out of it. Over here, there's only one arrow going into each one. That's one-to-one. Every one of them has an arrow coming into it. That's onto. So it's one-to-one and onto, which makes it a one-to-one correspondence. Let's look at the other opportunities. What's wrong with this third one?
Not a function.
It's not a function because the 4 has 2 arrows coming out of it. What about this one? It's not a function because the 4 doesn't have any arrows, does it? Now, the inverse of which function below is a function? Now, first of all, what are we looking for when we're looking for an inverse?
One-to-one correspondence.
It's got to be a one-to-one correspondence, yes, because when you reverse it, now the one arrow coming into each element says, okay, it can be a function. The other thing, so though it says, is every element must have something coming out of it. So therefore, it's got to be a one-to-one correspondence. So this first one, not a one-to-one. We have 2-to-1 here. Okay. So that's not it. What about the second one? It is, isn't it? Remember, I think these are the same ones from the previous question. If I put this over there, this would go to 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 there. I think it would be the same. Okay. The next one is not a function in the first place, and the last one's not a function in the first place. So that's the answer. Okay, any question on functions? We're in pretty good shape on functions? Well, that's going to wrap it up for today because we're right at time. So on Wednesday then, we'll start looking at graphs.